Okay, good morning to all of you. I welcomes to all in our lecture series on statistical mechanics. That is your core paper 14 belongs to 6th semester BSc syllabus. In our last class, we have been discussed about comparison of three ensembles. That is your microcanonical, canonical, and grand canonical ensemble. And this is your last topic of your second unit. And today we are going to start a new topic and a new unit. Okay, new unit, that is your unit 3, and the topic is your radiation. Okay, basically here in this topic we are going to be discuss thermal radiation. Okay, so as per the definition here, the radiation is a physical phenomenon that is the energy transported without the active contact or participation of the intervening medium. In this process, a medium is not required. Example, your transfers of energy, that is your heat energy, in solar system, interstellar space, and the galaxies. So, to transmit the thermal radiation or any kind of radiation, no need to require the medium. Okay, it can without medium it can be propagated from one point to another. In today class, we are going to discuss only the properties of the thermal radiation. Okay, and here, however, for conduction and convection, medium is required uh, to flow of heat energy. Okay, to flow of energy, or you can write heat energy, no problem. Actually, this unit or this chapter, you can say, is based upon only thermal radiation. Now we have to go for the properties of thermal radiation. So these are the points or properties. One by one we are going to discuss. Thermal radiation considered as electromagnetic radiation produced by thermal motion of charged particles in the matter. Okay, uh, due to the thermal motion of the charged particle in the matter, whatever the radiation it can be give towards its surrounding, that radiation will be called as your thermal radiation, and thermal radiation is accepted or considered as electromagnetic wave. And all bodies that may be any metal or any insulator or anything, all the materials radiates energy above 0 kelvin. So all bodies above 0 kelvin, this is most important point. All bodies above 0 kelvin radiate thermal energy. Okay, then third point is your so third point is, as this is electromagnetic wave, as thermal radiation is a electromagnetic wave, so hence thermal radiation travels through vacuum with the velocity of light. It is obvious. Then fourth point, thermal radiation travels in straight line and obeys the law of reflection, refraction, and also exhibits the phenomenon of interference, diffraction, and polarization of light. So thermal radiation, as the thermal radiation considered as electromagnetic wave, it is propagating with the velocity of the light. Also, it obeys all the characteristics whatever uh, the light obey. Okay, whatever the what we can found from the characteristics of the light, or the characteristics of the light, all the characteristics of the light obeys by the thermal radiation. Okay, and the thermal radiation not to be detected by human eye, but it can be used, or bolometer is the instrument used to detect the thermal radiation. This is important that you have to remember oftenly in your exam. This is the most important short question. What instrument used for your to detect the thermal radiation? Okay, next point is your thermal radiation consists of quanta or photons of energy h mu, where h equal is your Planck constant, mu is the frequency of the radiation. Okay, almost all characteristics same with your light. the quantity of heat radiated per second depends on the nature of the emitting surface, its surface area, and its temperature. This point is most important, which will be required in our further in our forthcoming classes. Okay, so here one material is radiating the energy. Suppose this is the material. This material radiating energy or heat energy or thermal energy, that radiated energy, the quantity of heat radiated, how much energy this material radiates, is depends on the area, how much area we have been considered. Suppose this much area per second, how much energy is going to be radiated. If we have to consider whole area, obviously large energy is going to be radiated. So quantity, that means amount of heat radiated per second by a body, depends these three parameters, which is most important, that you have to remember always: nature of the body, nature of the substance or body or emitting surface, its surface area, and its temperature. So suppose this is your metal. Okay, the amount of heat thermal energy radiated per second will be different if this will be a plastic or it will be a rubber. Suppose we are going to consider is another material made up of plastic. If we are going to consider same area, the radiation by this material per second will be different than this, because the materials are different. Now we are going to consider same material, say this material. From this area, how much radiation is going to be radiated per second? If I am going to consider large area, the radiation will be different, the radiation will be different, heat radiation. And suppose this material is at room temperature. I'm holding this in my hand, man, that means it is in the room temperature. So what will be the radiation now from this surface, thermal radiation? What will be the thermal radiation from the surface now? If I am going to increase the temperature, the radiation will be large, because if you are going to consider, suppose a iron you have to put uh, suppose this material, you can just consider this material and put it into a burning fire. Okay, burning fire, and take out. Now whenever you are for sometimes you just put it in the burning fire, and it will be gain some heat energy, and its temperature is going to be increased and take out. Now before and after radiation per second will be different, because the temperature has been changed, temperature is increased. So if the temperature is going to be increased, the heat energy is going to be increased. The temperature increase, heat energy is going to be increase. Or so we know that energy is nothing but h mu. Okay, if energy is increased, so obviously the frequency, whatever the radiation is coming out at the higher temperature, that corresponding frequency also will be increased. If frequency will be increased, the corresponding wavelength is going to be decreased. The same thing I have written in the next point. So yes, the next point, that is your V third eye. The nature of the thermal radiation depends upon the temperature. At the low temperature, a body emits radiation of longer wavelength. What I explained here. If I am going to increase the temperature, heat energy will be the radiation of heat energy. This is not the radiation. The radiation of heat energy will be increased, and energy, we know that h mu, as heat energy is nothing but your quanta, or your it is uh, made up of quanta or photons. So if mu will be increased, so obviously energy is going to be increased. So at higher temperature, heat energy, radiation of heat energy will be increased. Radiation of heat energy increases means the corresponding frequency increases. If corresponding frequency increases, corresponding wavelength decreases. So the nature of the thermal radiation depends upon temperature. At low temperature, the body emits a radiation of longer wavelength. Of longer wavelength. Here you can see that here temperature I increased, wavelength decreased. Likewise, we are going to consider temperature is going to decrease. That means suppose this is your this material is in room temperature. Okay, now put it in a cold bath. So its temperature decreases. If temperature decreases, the radiation of heat, the radiation RHE means radiation of heat energy also is going to be decreased. If radiation is decreases, the energy is nothing but your h mu corresponding. Frequency decreases. If frequency decreases, that means wavelength increases. That we know that your uh, because we know that V equal to lambda by T or lambda into F. So if frequency will be increased, wavelength corresponding wavelength will be decreased. That we know. So here the nature of the thermal radiation depends upon the temperature. At low temperature, a body emits radiation. This is also another most important point that you have to remember. If temperature is going to be decreased, wavelength is going to be increased. Both are inverse proportional. Body emits radiation of longer wavelength. Temperature uh, uh, increased, wavelength decrease. Temperature decreased, that means for the low temperature decrease, wavelength is going to be increased. In general, thermal radiation range approximately 8000 angstrom wavelength range. Here in general the wavelength, okay, we just corrected wavelength of thermal radiation in the range in the range around approximately 8000 angstrom to 0.4 millimeter. 0.4 millimeter. This is around your IR radiation, IR or above that wavelength. Okay, 0.4 mm wavelength. Now, these things we know that equilibrium we can found when the exchange of the heat in between body to its surrounding is going to be equilibrium. But here one one word has been used, that exchange of heat between a body and its surrounding continues till a dynamical thermal equilibrium obtained. Dynamical thermal equilibrium obtained. That means suppose this is a body and this is your surrounding. So if surrounding is at low energy, then the energy is going to transmit from here to here, from this body to the surrounding, and that energy exchange, that means this, suppose this is at higher temperature, this this body at higher temperature and its surrounding is at low temperature. So if this body is radiating higher energy to the surrounding, obviously some lower energy also this body is absorbing from the surrounding. So radiating energy to the surrounding and absorbing lower energy from the surrounding, this is going to be continue. Higher energy is given to the surrounding and lower energy taken from the surrounding. So this dynamics is going to be continue when a equilibrium amount of heat energy is going to be radiated to the surrounding. Will that much amount of heat energy is going to be taken from the surrounding? If both are same, then we can say that a equilibrium condition, dynamics means both are in motion condition given to the surrounding, taken from the surrounding. Okay, both are same. So a dynamic thermal equilibrium obtained, right? The thermal radiation produce heat when they are absorbed by a body. A good absorber are good radiator and vice versa. This is also another important point. So if we are going to be give some thermal radiation to this body. Suppose this is a body, we given some thermal radiation upon this, its temperature is going to increase. Suppose initially it was temperature T1, after getting some thermal radiation from outside, its temperature became T2. T2 will be greater than that of the T1. Temperature is going to be increased whenever it is going to be take radiation, heat radiation, thermal radiation from the outside. Okay. And a good observer means which material is going to be absorbed more quickly heat energy from the outside, that material can be radiate more quickly to the surrounding. Suppose these are the two materials, this one and this one. Suppose I given suppose 10 amount of heat to this and 10 amount of heat to this. Okay, suppose the 10 amount of heat absorbed by this material and taken, suppose 2 minutes. Okay, 2 minutes, but this material taken same amount of energy, the time taken by 1 hour. That means this material absorbed more quickly heat. That material also good radiator. Within quickly, if quickly also this material is going to be radiate energy to the surrounding. So they are absorbed by a body. The thermal radiation produce heat when they are absorbed absorbed by a body. So heat means if it will be absorbed thermal radiation, then it will be hotter and hotter. Okay. They are absorbed by a body. A good observers are good radiator also, and vice versa. When thermal radiations fall on a body, they are partially reflected, absorbed, and transmitted. That is, this is also one of the important. Suppose here we are going to consider. Suppose this light is falling upon this. Suppose consider this is your thermal radiation is falling upon this material. You can see that some of the uh, radiation is reflected, right? Some of the transmitted, here you can see this can be visible, means some of the light or some of the radiation transmitted and some of the energy transmitted by this material. So if we are going to apply a x amount of heat radiation upon a material, then it is used as uh, reflection, absorbance, and transmit. That means x total radiation energy will be R plus A plus T. Okay, so here the same thing it has been written on the base of the definition, that reflectance. Now we are going to consider reflectance. Reflectance is represented by small r. Okay, what is the meaning of the reflectance? The ratio of the amount of thermal radiations reflected by a body in a certain time. Most important, in a certain time, amount of thermal radiation reflected. Suppose thermal radiation incidents, amount of thermal radiation reflected from this surface in a certain time. Suppose in 1 minute. Suppose we are going to consider 1 minute. Suppose 1 minute. Okay, in 1 minute, some of the energy has been reflected from this surface. Suppose that is your R. Okay, to the total amount of incident thermal radiation falling upon the body in the same time is called reflectance. That is, reflectance is represented by R equal to R by Q. That means, suppose what I told, that Q amount of thermal energy incidents upon this material for 1 minute. Okay, Q amount of energy has been incidents upon this material for 1 minute. Let R amount of energy, thermal energy reflected in the same time 1 minute. Okay. So now reflectance of this substance will be how much radiation reflected in that 1 minute, how much energy incidence in that 1 minute. This is your nothing but called as the reflectance of the substance, right? In the similar manner, we can define absorb, absorptance. Absorptance, which is represented by small a, the ratio of amount of thermal radiations absorbed by the body in a certain time to the total amount of thermal radiation incident upon it in the same time is called as absorptance of that material. Let suppose q amount of energy has been incidence, q amount of energy incidence for 1 minute, and that exactly in 1 minute how much energy it has been absorbed. It has been absorbed. Let the a amount of energy has been absorbed in that 1 minute, then absorptance of that material will be equal to small a equal to a by q, amount of energy absorbed in 1 minute and divided by amount of energy incidence, or the total amount of energy incidence for that 1 minute, or this material exposed for 1 minute in this radiation, how much energy has been absorbed. Let this is a in that 1 minute, a by q is nothing but is your a, that is your absorptance, a equal to a by q. Now we have to define transmittance. So transmittance means how much energy is going to be transmit in that same 1 minute. The as per the definition, the ratio of thermal radiations transmitted, let T, by body in a certain time to the total amount of thermal radiation incident on it in the same time is called the transmittance. That means suppose for the 1 minute it has been uh, exposed with this radiation. Suppose uh, T amount of energy has been transmitted in that 1 minute. How much energy has been incidence in that 1 minute? Q. So this T by Q will be nothing but your transmittance of that material. So here one thing you maybe conclude that Q amount of energy has been incidence. How many for how much time? For 1 minute. Okay. Your reflected energy for this 1 minute is R. Absorbed energy is A. Transmitted energy or radiation is T. And corresponding reflectance is how much? R by Q. Absorbance. Absorbance is your A by Q. Transmittance T by Q, which is represented by this is small r, this is small a, this is small t. Now this whole energy Q, if I am going to consider 1, then R plus A plus T will be nothing but 1, obviously, right? So here this is a note that you have to remember. The reflectance R, absorptance A, and transmittance T of the body depends on the nature of the surface of the body, the frequency of the incident radiation, and mathematically what I explained, your reflectance plus absorptance plus transmittance will be equal to 1. So the total amount of energy, whatever incidence, part of the energy has been reflected, part of the energy absorbed, and part of is transmitted. If I'm going to add this R plus A plus T, R plus A plus T, then it will be equal to Q. Okay. So here one thing also we can write. See this will be R plus A plus T will be 1, and capital R plus capital A plus capital T will be equal to Q. So this is the two important point that you have to consider. These two points or phenomenon will be required in our future classes. So nature of the surface of the body. So this reflectance, absorbance, and transmittance depends upon the nature of the body. I'm going to give you an example. See, this is the material. Okay, this is the material has transmittance. reflectance and absorbance. Okay, if I'm going to consider this one, if I'm going to consider this material, so there is reflection, absorbance is there, but transmittance is not there. Transmittance will be 0. That means for this material, I have to write R plus absorbance is that A plus T will be how much? 0 will be equal to 1. That means only reflectance and absorbance we are going to get, and we are not going to get any type of transmittance. So hence, nature of the surface of the body, this on the base of the nature of the surface, reflectance and absorbance and transmittance depends, and also frequency of the incident radiation. How, why frequency of the incident radiation? Here I am going to show you that suppose this is your light, suppose this is your white light, or suppose this is your radiation for a particular frequency. Amount of whatever the amount of energy transmitted, if the frequency will be increased, that much more energy can be transmitted, because if higher energy can be penetrate more, so transmittance will be more. So hence, these 2 points, that nature of the surface of the body, both this reflectance, absorbance and transmittance depends upon the nature of the surface of the body and frequency of the incident radiation. So thank you so much for watching this video. Pause the video and write down the note and ready for the next class. Next class we are going to discuss black body radiation. Okay, thank you so much. Thank you.